Loop-the-loops and centripetal force. You may have seen this at circuses with like motorcycles going inside like a round cage ball, or the roller coaster example at an amusement park when the roller coaster goes upside down. Making a loop. The key to making a loop is your speed. At the most critical spot, which is when you're directly upside down as pictured in this little diagram, and looking at the free body force diagram in that situation, assuming no friction here, when you're completely upside down, there's the force of gravity, always, and the normal force, in this case the force exerted by the track, which is always perpendicular to the road or surface that you're on. So the diagram here is good. I'll relabel the force of gravity, I'm going to call W, and the force of the track I'm going to call F sub n, the normal force. The centripetal force, when you make it with ease, in other words you have excessive speed, is the net force. The net force is always in a circular motion towards the center of the circle. It's just the sum of these two forces because they're in the same direction. Now, the same thing applies when you just barely make it. You have essentially F sub c equals W plus F sub n. But what happens is when you're just barely making it, you're almost ready to fall off the track. In other words, this F sub n is going to go to 0. That's when you're just barely falling off the track. Or to simplify, F sub c equals W is the condition for when you just barely make a loop. And then if you plug in the definitions of these concepts, F sub c is mv squared over r, and weight is mg, and solve for v, multiplying both sides by r, we have mv squared equals mgr. You can cancel out the m's on both sides, take the square root of both sides, and you end up with v equals the square root of gr. That's the condition for just barely making a loop. If you look at it closely, you can see that there's no mass involved. It doesn't really matter what your mass is. All that matters in making a loop is the radius of the loop and gravity, which on Earth is constant at 9.8. So let me summarize once again at the top there. That's the hardest part. The algebra is not too bad. But when you're just barely making it, your normal force, you're just barely touching the track. When you make it with excessive speed, the track is helping hold you in. So the F sub n will not be 0. Now, what about when you're at the bottom of a loop? Let me extend this circle as best I can. When the car is at the bottom of the loop, and this diagram is not the greatest, but here's the car at the bottom of the loop. Once again, when you're going around the loop, at the bottom, weight is still a factor. It's always straight down. But now, like always, the normal force is perpendicular to the surface you're on. In this case, it points up because it's perpendicular from the road or track to the car. The normal force will be bigger than the weight. When you're in the upside down position, the normal force can be less than or equal to or greater than the weight. And when it goes to 0, you have that condition I just went through with the barely making it. But when you're at the bottom, F sub n has to be bigger than weight because the net force has to be towards the center of the circle. When you're going in a circle, there's always a centripetal force, a net force towards the center. The same equation will apply. F sub n, or F sub c, will be equal to, well, we have to make an adjustment here. It'll be F sub n minus W. Big force minus small force, consistent with our F net equals ma. Your net force has to be the one that's towards the center here, centripetal. So F sub n has to be bigger to cause the acceleration to be towards the center. Let's apply this with some examples. Many of you probably played with Hot Wheels cars when you were a kid, and maybe you had a loop-the-loop for the Hot Wheels car. Little car came down, started high. We could also relate this to our GPE to kinetic energy problems from 2 units ago, conservation of energy. Car comes down, the GPE transfers to kinetic energy. The car needs enough speed. If it doesn't have enough speed, it does not make the loop. We're looking for the minimum speed to make the loop. And the critical point, once again, is this spot up here at the top. I didn't do a good job of the tires there. Car is upside down, and the condition is, at that point, it's just about ready to come off the track. The normal force has gone to 0, and all we have is the weight force as our centripetal force. I went through all the math on the previous page here. It results in the formula or the equation V equals the square root of GR, the condition for just barely making a loop. The speed that the car needs at that point, it would actually need more speed than that at the bottom because it loses speed as it goes up the loop, losing kinetic energy and gaining GPE. We're not going to calculate that here. But in this case, we have the square root of 9.8 times the radius, which is 0.15. And you do want to have this in meters. I divided the 30 by 2 because the diameter is 30, the radius is 15 centimeters. In this case, this car needs a speed of 1.2 meters per second at that upside down location to make this loop. It would need more speed than that at the bottom. All right, but what if our car was making it with ease? If our car was making it with ease, at the top of the loop, the diagram for that car, then it would have, and I'm not going to draw the track this time, it would have the weight vector still, and now it's going to have the track vector force, which is perpendicular to the track, and that's F sub n, or force of track, normal force from the track. F sub n could be bigger than, less than, or equal to W. We don't know. The faster it goes, the bigger F sub n is. The slower it goes, F sub n can go to 0, and that was the case we just explored in number 5 and with the theory on the previous page. But F sub n could be any size bigger with greater speed. Anyway, as we saw before, when you're making it with ease, F sub c, the centripetal force, is the net force, will be the sum of these two forces because they're both in the same direction. And then we just plug in all the conceptual definitions. F sub c is mv squared over r equals weight is mg plus F sub n. Plugging in now, the mass of this car is 39 grams. That would be 0.039 kilograms times the velocity. Now the car has excessive speed. It's beyond the 1.2 meters per second of speed it needed. So the track is helping to contain the car now. The radius is still 0.15 meters equals the mass of the car, 0.039 kilograms times 9.8, I'll use a little bit more accurate number here, plus F sub n. So F sub n is the force the track exerts on the car. If you go to your calculator and just plug in all the numbers, F sub n comes out as 1.7 newtons. And that's the force the track exerts on the car. All right, when the car is at the bottom of the loop, and you'll see that these diagrams are very good in guiding the problem. And I'd like you to draw these diagrams, these free body force diagrams. When you're at the bottom of the loop, I'm just drawing the car right now, but you have to envision that it's at the bottom of the loop. The weight vector, as we know, is always straight down, W. When the car is at the bottom of the loop, however, the track is now exerting a force up, perpendicular, F sub n, because it's always perpendicular to where the car is touching the track. And F sub n has to be bigger than W because we have to have a net force towards the center of the circle. In other words, if we look at our net force equation, F sub c is the net force, equals F sub n minus W. That's going to be the hardest part in these problems, is getting this straight here. When it's F sub n plus W, or W minus F sub n, or F sub n minus W, I drew the diagram to scale, but we know the center of the circle is above the car. If the car is at the bottom of the loop, the center of the circle is up here above the car. The net force has to be towards that point because the acceleration has to be towards the center of the circle. So it's always big force minus small force to get the proper orientation of the vector summation here to get the net force. So now it becomes fairly easy mechanical. F sub c, once again, is mv squared over r equals F sub n minus mg. Let me plug the numbers in. I need a little space here. I'll switch to black for a second. So I'm going to plug in now 0.039 kilograms times, if the car is at the bottom of the loop going the same speed, 2.8 meters per second squared. Once again, the radius is 0.15 meters equals F sub n minus the mass 0.039 times 9.8. All right, you run that through your calculator. The normal force, which will now be bigger than it was before, is 2.4 newtons. The normal force at the bottom of the track. One more example. Imagine yourself in a car going down the road at 30 meters per second, which is fairly fast, around over 60 miles per hour. Now when you go over a bump, you kind of feel like you lift out of your seat a little bit. Same thing happens when you're in a roller coaster. You go over a bump and you kind of feel like you're lifting out of your seat. And the faster you're going, the more you feel like you're kind of getting maybe a little bit airborne almost. Let's look at the free body diagram for a person going over a bump or the cresting a hill in a roller coaster. Here's my person. These diagrams are going to be very important. Here's the person. What forces are acting on this person? Well, you have your weight, which is always straight down, W. And you have the seat, which is touching you and pushing up. Now, when you're on a level road, your normal force from the seat is equal to your weight. You have no net force up and down. However, when you're cresting this bump, you're on a hill, right? Let me make a small sketch here to the right. Here's the hill. So this is not to scale from the first free body diagram of the person here on the left. When you're going over the hill, okay, you're in your car. That's supposed to be you in the car. You're at the top of a circle, and the center of the circle is down here, lower than you. So as you're going in a circular motion like this in the car, you must have a centripetal force towards that direction because you're accelerating in that direction as you're going over a hill. Whenever you're in circular motion, you have a centripetal force and a centripetal acceleration. What that means here is, and this is the toughest part of this, is that your normal force as you're cresting the hill, F sub n, is less than your weight force because you have to have a net force towards the center of your circular motion because you need acceleration, or you have acceleration towards that center dot. Once you have that all figured out, the rest becomes fairly easy. F sub c equals, that's F sub c is the net force, W minus F sub n. Big force minus small force. They're in opposite directions, but the bigger force, the net force, F sub c, has to be towards the center of the circle. And now it's a matter of plugging in. So we've gotten past the hard theoretical stuff. You may need to rewind this and think about that one, but here's now all mechanical. mv squared over r equals mg minus F sub n, the normal force from the seat, which is what you feel like you weigh. The thing you're sitting on or holding you up is what you feel like you weigh. So your mass here, well, we have the weight of 150 pounds. Let me go back up to the top here. If we know that 1 pound is 4.45 newtons, then the 105 pounds becomes, if I do the math here, around 668 newtons. That's what this person weighs, 668 newtons. And if you divide by 9.8, it's a little bit more accurate here. If you divide that by 9.8, that's 68 kilograms. This is a 68 kilogram person. All right, so the mass is 68 kilograms times, when you're cresting this bump, the very top of the bump, 30 squared over the radius, which is 100, equals the mass, 68, times 9.8, minus F sub n, which is what you feel like you weigh. It's support force from the seat. If you run through the calculations here, you end up with F sub n equals 54 newtons, which is close to zero, actually. You're almost coming out of your seat. That's about 12 pounds. You're going to feel like you're about 12 pounds momentarily. You feel very light. You feel like you're almost coming out of your seat. Part B now, I'm going to squeeze it in over here at the right. When you're at the bottom of a hill or going through a dip, the free body diagram, once again, you're sitting in a chair, so you have to envision this. Think about this for a second. When you go through a dip, like if you're going really fast in a car, here you're going like almost 80 miles per hour, you kind of get pushed, you feel like you're getting pushed down into the seat. What you're actually doing is being pushed up by the seat, more so than you were before. But when you're at the bottom of this dip, the center of the circle is above you now. I'll put a little dot above this person's head, representing the center of the circular motion. All right? So, but you're sitting in a seat. What forces are acting on you? Well, weight is always pulling you down, W. But now when you're in the bottom, at the bottom of this circle, the normal force by the seat is bigger than W. This is the hardest part about this problem. You may need to think about this and ask me questions if you're confused. But the net force has to be towards the center of the circle. F sub n has to be bigger than the weight. And F sub n is what you feel like you weigh. Your actual weight doesn't change because that's based on gravity and the Earth's force of pull pulling on you. All right? Once you have this figured out, it's now fairly straightforward at this point. And that is F sub c is the net force equals the big force, F sub n, minus the smaller force, W. The net force, when they're in opposite directions, you have to subtract them. So there's how this plays out in this case. Then you just plug in mv squared over r equals F sub n, which is the feeling you feel like you have of your weight, minus mg. Now we're going to plug in. I plugged all the numbers in, keeping in mind we're going a little faster now at the bottom of this dip. So whether you're in a car or a roller coaster, you're going to feel like you're being pressed harder into the seat because the seat force is going to be greater going up now, even though your weight didn't change. So here are all the numbers plugged in. If you run through the calculation, you end up with F sub n, the normal force that feels like what you weigh is about 1,500 newtons. That's what you feel like you weigh. Now in this case, at the bottom of this dip, that is around 340 pounds. You're going to feel twice as heavy as you normally feel. So, centripetal force, it's a net force towards the center of circular motion.